Good morning, Internet. I am Matt Booyak, and in this video, we'll be taking a look at the 55th problem from the Project Euler Problem Archive. Now, this problem asks a question about Lychrel numbers, and in particular asks us to find how many of these numbers exist under 10,000. And to define what a Lychrel number is, it describes this process whereby we start with some number and reverse it and add it to itself to get some other number. And observes that with some starting numbers, eventually they will reach a palindrome, while other numbers appear to never reach a palindrome, no matter how many times this process is repeated. And the numbers which never reach a palindrome are Lychrel numbers. Now, we have a little bit of a theoretical difficulty here because the existence of Lychrel numbers has not even been proven in base 10. It's been proven for some other number bases, but not base 10. And so how are we to solve this problem if the thing we're looking for has not even been proven to exist? Well, the problem gives us a little bit of an out by saying that any number which is less than 10,000 and fails to become a palindrome in fewer than 50 iterations should be assumed to be a Lychrel number. And so this also suggests an algorithm for solving this problem. We're just going to try each of the numbers less than 10,000, repeat this process until we reach 50 iterations or until we have a palindrome. And if we get through all 50 iterations without finding a palindrome, then we increment our total count of Lychrel numbers. Now, this pile of digits down here may have given it away, but the numbers involved here can get rather large. To get some intuitive sense for why this is the case, if you assume that a number and its reversal are about the same size, that would mean that the number would roughly double each time you repeat this process, which means it would grow exponentially. Now, a number and its reversal aren't exactly the same size, but they're at least the same order of magnitude. So it's not a bad way of thinking about it, I think. In any case, we're going to need our big integer class, which we just did a video on yesterday where we added the ability to convert to and from a string, specifically in preparation for this problem. Now, before we get started, there's just one more aside that I think is I found amusing. Apparently, I thought Lychrel numbers would be named after the mathematician who discovered them. Apparently, they're actually named after that mathematician's girlfriend, who was named Cheryl. Cheryl being an anagram for Lychrel. You know, some people get flowers and chocolates. Other people get you a mathematical object that's conjectured to exist in base 10 but hasn't been proven yet. To each their own, I suppose. In any case, let's get into it. As usual, we will copy our template directory to make our problem directory, enter our problem directory, and open our main.cpp. Now, I think it's worth just refreshing our memories about that big integer class. So let's go over and take a look at that. In the last video, we added this method here for initializing a big integer from a string, and also this method down here to convert a big integer to a string. So we'll definitely be making use of those. Also, you'll see that we have the ability to add a big integer to another big integer, which will also be required. Okay, so let's go back to our main.cpp, and we're going to want to say include BigInt.h. We'll also need to update our makefile to link in our number theory library, which has our big integer class. Okay, so now in our main here, let's say for int I n equals 1, n less than 10,000 plus n. And let's assume that we have some function is Lychrel. So we'll say if is Lychrel n plus solution. We'll need to actually declare that variable. So let's say int solution equals 0. Down here, printf solution equals solution. Okay. So obviously the main part of our solution is going to be this is Lychrel function. So let's go up here. So we'll say bool is Lychrel int n. Okay, so we're going to need to store our integer as a big int. So let's say big int n, and we're going to initialize that with the small integer n. We're going to need to keep track of the string representation of both n and its reversal in order to efficiently check if we have a palindrome, and also in order to do the addition step. So let's say std string, we'll say nstr, and then we'll say std string rev str. And let's initialize this with toString n. We'll need to actually include string. And while I'm at it, we're going to need to be able to reverse our strings. And so let's include algorithm as well. Okay. And so try to think if we should do the reversal here. Let's hold off on that. Okay, so let's say for int I equals 0, I less than 50 plus I. So this is going to be doing our 50 iterations. And we're going to need to start off by adding, okay, so I think we will need to do the reversal ahead of time because we need to immediately add, we need to do the addition step before we check to see if our number is a palindrome. One clarification that they have here in the problem description is that there are some palindromes which are considered to be Lychrel numbers, and that's because you have to do the reversal and addition step first before you check if your number is a palindrome. Starting off with a palindrome doesn't satisfy the requirements to not be a Lychrel number. Okay, so let's do std reverse. Let's begin with initializing this with nstr, and then we'll say reverse revstir.begin revstir.end. Okay, and so now we want to initialize a new big integer that is the reversal of n. So we'll say BigInt nRev is going to be initialized with revstir. And then we can say n.add nRev. Okay, now we need to update our strings. So we'll say n_stir is equal to n.toString. And actually, yeah, I think that should be fine. So then we'll say revstir is equal to nstir. And then as before, in fact, we can just copy this line up here. To get our reversed string. And then we'll say if nstir equals revstir, that is, we have a palindrome because the reversed string and the original string are the same, then we say return true. Return false. That is, if we have found a palindrome, it is not a Lychrel number. Okay, and then after 50 iterations, if we have not found a palindrome, we say return true because our number is assumed to be a Lychrel number. All right, let's go back to our shell and build. It took quite a while to build. In any case, let's, you know what, let me, before I do that, I was messing around a little bit with the number theory library earlier. Let me just make sure that this is actually up to date. Okay. And let's run. And we have a solution 249. So let's go back to the archive and sign in. The website's being very slow this morning. This is somewhat concerning. It seems like perhaps, okay, so, oh, there we go, okay. For a moment there, I was worried that Project Euler had gone down at a most inopportune moment. It seems to be back up now. Let's see. Okay, now we are signed in. Let's go to the second page and go down to problem number 55. And we see that that does indeed match our answer. So as always, thank you for joining me in this video. In the next video, we'll be doing problem number 56. I'm still working on that video for problem number 54, where we'll be looking at poker and how to evaluate poker hands programmatically. So you can look forward to both of those things in future videos.